What makes stars shine and allows our own sun to burn for billions of years? In 2003, the Franklin Institute honored three giants of astrophysics, John Bacall, Masatoshi Koshiba, and Ray Davis, for their discovery of elusive particles called neutrinos, the first direct proof that stars are powered by nuclear fusion. But their discovery raised a new mystery that persisted for 3 decades, until Yoji Totsuka and Arthur McDonald stepped onto the scene. And while they grew up as competitors working on opposite ends of the Pacific Ocean, their parallel lives always seemed destined to meet. Born just 1 year apart, Yoji Totsuka and Art McDonald both had an early curiosity that they took out on their parents' appliances. McDonald tried to find out what makes things tick by dismantling clocks as a youngster, and for Totsuka, it was radios.
My parents were not very happy because they couldn't listen to news or music.
Each followed that curiosity all the way to the most basic constituents of matter, the world of particle astrophysics.
I loved it, the application of mathematics to really understand physical laws, and the fact that you could calculate something, and lo and behold, that's exactly how it worked.
Both were inspired by the scientists who discovered solar neutrinos, evidence of the reactions in a star's core that make life on Earth possible. McDonald worked alongside John Bacall at Caltech, and Totsuka was mentored by Toshi Koshiba at the University of Tokyo, spending tireless weeks at a particle detector in a remote mountain zinc mine.
The life was very tough, and even miners were sorry that we worked so hard under such a primitive condition.
Their predecessors' groundbreaking work detecting solar neutrinos gave conclusive proof of what powers stars. But it also left Totsuka and McDonald with a puzzling new problem, because detectors were counting far fewer solar neutrinos than expected. While the standard model of particle physics included solar neutrinos and 2 other so-called flavors of neutrinos, it also predicted that neutrinos had no mass and could not change flavors. If the missing solar neutrinos were eluding detection by actually changing flavor, then the standard model, which describes the origin and workings of the entire universe, was wrong. But if Totsuka and McDonald were to investigate this, it would take more sensitive detectors. In 1991, Totsuka led the construction of a new underground detector that could also see a flavor of neutrino produced by cosmic rays. In 1998, his team presented evidence that those neutrinos change flavor depending on how far they travel.
I still remember that the audience, people, applauded, clapped their hands for more than 10 seconds or so, just like a music concert. So that was the moment that the world accepted our discovery.
But that wasn't concrete proof that neutrinos produced by stars did the same. McDonald went to Queen's University in Canada to take on the challenge of building the Sudbury Neutrino Observatory. More than a mile below an Ontario nickel mine, this new solar neutrino detector added the missing pieces to the puzzle. McDonald and Totsuka joined forces, shared their data, and in 2001 they announced conclusive proof that solar neutrinos change flavor, upending the standard model of particle physics and forcing textbooks to be rewritten.
We really set out to do some textbook science, and we have managed to do that, and we hope that we can do even more textbook or very basic science.
They should get that chance. Their fundamental discoveries have profound impacts on our understanding of the basic makeup of the universe. But their work also leads to new questions. Their calculations indicate that today, at least one other unknown fundamental particle awaits discovery, bringing both scientists full circle to where they started, investigating the unknown and solving mysteries.
Science is based upon curiosity. If there is a mystery, then I would like to find out the solution to that mystery.
The 2007 Benjamin Franklin Medal in Physics is presented to Yoji Totsuka and Arthur McDonald for discovering that the 3 known types of elementary particles called neutrinos, change into one another when traveling over sufficiently long distances, and that neutrinos have mass.